Somewhere in the darkness beyond our galaxy, beyond the familiar spiral arms of the Milky Way, beyond even the nearest clusters of galaxies, there exists something so large that it makes our entire cosmic neighborhood look like a grain of dust drifting through a cathedral. It does not shine like a star. It does not explode like a supernova. It does not roar like a black hole tearing matter apart. And yet, it may be the largest single structure we have ever identified in the observable universe. For most of human history, the night sky felt intimate. A dome of scattered lights, a canvas of myth and story. We believed the stars were fixed, eternal, perhaps even arranged for us. Then we learned that those stars were suns. Then we learned that those suns were only a tiny fraction of a galaxy. Then we learned that our galaxy was one of hundreds of billions. Every time we thought we had reached the edge of scale, the universe quietly extended it. But what if I told you that even galaxies, vast, luminous cities of hundreds of billions of stars, are not the largest meaningful structures in existence? What if I told you that galaxies themselves are merely threads in something unimaginably larger? A structure so enormous that light, traveling at the ultimate speed limit of the cosmos for billions of years, would still struggle to cross it. This is not science fiction. This is not theoretical abstraction. This is an observation. We are about to explore the largest object we have ever found in the universe, a structure that challenges our understanding of how matter organizes itself, a discovery that forces cosmologists to reconsider the fundamental assumptions about the large-scale uniformity of the cosmos, and a structure so immense that it stretches our imagination to the breaking point. Tonight, we travel outward, beyond planets, beyond stars, beyond galaxies, beyond clusters of galaxies, into the deep architecture of the universe itself. Before we begin this journey into the largest object ever discovered, make sure you subscribe to The Boring Universe for long-form explorations like this one. If you enjoy deep cinematic science documentaries, take a moment to like this video and leave a comment below, and tell us which part of the country are you watching from. Now let's begin. To understand the largest object ever discovered, we must first confront a fundamental problem scale. The human mind evolved to comprehend distances measured in meters and miles. We are comfortable with the height of mountains, the width of oceans, the distance between cities. Even the scale of a planet, though vast, can be rendered understandable through maps and images. But the universe does not operate in units that fit easily into human intuition. Its scales are exponential, layered, and profoundly indifferent to the limits of imagination. Let us begin close to home. The Earth spans roughly 12,742 kilometers in diameter, large by terrestrial standards, but modest when compared to Jupiter, which is more than 11 times wider. The Sun, in turn, dwarfs Jupiter, stretching nearly 1.4 million kilometers across. More than 1 million Earths could fit inside the Sun. Yet our Sun is not unusual. It is a middle-aged, medium-sized star in a galaxy filled with hundreds of billions of stars, many of which are significantly larger. Some red supergiants are so vast that if placed at the center of our solar system, their outer layers would extend beyond the orbit of Mars, perhaps even Jupiter. And still, stars are not the dominant structures of the universe. Our solar system orbits the center of the Milky Way galaxy, a spiral structure approximately 100,000 light-years in diameter. A light-year, the distance light travels in 1 year, is about 946 trillion kilometers. So when we say the Milky Way spans 100,000 light-years, we are describing a structure so large that even light, traveling at nearly 300,000 kilometers per second, takes 100,000 years to traverse it from one side to the other. Yet the Milky Way is just one galaxy among an estimated 2 trillion in the observable universe. Galaxies are not scattered randomly. They are bound together by gravity into groups and clusters. The Milky Way, for example, is part of the local group, which includes the Andromeda Galaxy and dozens of smaller satellite galaxies. This local group spans roughly 10 million light-years. Clusters are larger still. Massive galaxy clusters can contain hundreds or even thousands of galaxies bound by gravity, embedded within enormous halos of dark matter and filled with hot X-ray emitting gas. These clusters span tens of millions of light-years. Beyond clusters lie superclusters, vast associations of galaxy clusters stretching across hundreds of millions of light-years. Our own supercluster, known as Laniakea, extends roughly 520 million light-years across. It contains around 100,000 galaxies, all moving within a gravitational basin defined by dark matter and cosmic flows. For a time, astronomers believed that superclusters represented the upper limit of cosmic structure. Beyond that scale, the universe was assumed to become homogeneous and isotropic, meaning that when viewed on sufficiently large scales, matter would be evenly distributed. This principle, known as the cosmological principle, underpins modern cosmology. It assumes that the universe, on the largest scales, looks roughly the same in every direction and location. This assumption is not arbitrary. It arises from observations of the cosmic microwave background radiation, the afterglow of the Big Bang, which appears remarkably uniform across the sky. Tiny fluctuations exist, but they are small, 1 part in 100,000. Those tiny variations seeded the formation of galaxies and clusters over billions of years. The cosmological principle is essential because it simplifies the equations that describe cosmic expansion. Without it, the universe would be too chaotic to model accurately. And so for decades, astronomers assumed that while galaxies cluster into ever larger structures, there must be a scale beyond which the distribution of matter smooths out. That scale was estimated to be around 300 million light-years. Beyond that, the universe should appear statistically uniform, and then we began mapping the universe in 3 dimensions. In the late 20th and early 21st centuries, large redshift surveys began charting the positions and distances of millions of galaxies. Projects like the Sloan Digital Sky Survey created detailed maps of cosmic structure, revealing something extraordinary. Galaxies were not merely clumped into clusters and superclusters. They were arranged in vast filaments and walls, separated by enormous voids. The large-scale structure of the universe resembled a cosmic web. In this web, galaxies trace out immense strands of matter tens to hundreds of millions of light-years long. Where filaments intersect, clusters form like knots. Between them lie voids, regions containing far fewer galaxies, sometimes spanning hundreds of millions of light-years. The universe, it turned out, was not smooth at the scales we expected. It was textured, patterned, almost architectural. One of the earliest hints of extreme large-scale structure was the discovery of the CFA Great Wall in 1989. Stretching roughly 500 million light-years in length, it was at the time the largest known structure in the universe. It forced astronomers to reconsider their assumptions about homogeneity. But it would not remain the largest for long. As surveys expanded and instruments grew more precise, even larger structures emerged from the data. The Sloan Great Wall, discovered in 2003, extended nearly 1.4 billion light-years in length. That is a structure so vast that if you tried to cross it at the speed of light, it would take 1.4 billion years, more than 10% of the current age of the universe. Each new discovery pushed the limits further. And with each discovery came an uncomfortable question. At what point does a structure become too large? Cosmologists define an object carefully. A galaxy is gravitationally bound. A galaxy cluster is gravitationally bound. But superclusters and walls are often not fully gravitationally bound as a single entity. They are patterns of higher density, regions where galaxies are more likely to be found. So when we speak of the largest object ever found, we are not necessarily referring to a single gravitationally bound system like a galaxy cluster. We are referring to the largest coherent structure, an arrangement of matter that spans a measurable region of space, identifiable against the cosmic background. As our observational tools improved, astronomers began using distant quasars, extremely luminous active galactic nuclei powered by supermassive black holes, as tracers of large-scale structure. Quasars can be seen across billions of light-years, acting like beacons that illuminate the distant universe. By mapping the distribution of quasars, researchers uncovered structures of staggering scale. In 2013, a team analyzing quasar data announced the discovery of a structure known as the Huge Large Quasar Group. It spanned approximately 4 billion light-years. To put that in perspective, that is roughly 1/10 the diameter of the observable universe. A structure 4 billion light-years across strains the cosmological principle. It approaches the scale at which the universe is supposed to become homogeneous. And yet, even that may not be the ultimate record holder. As new data accumulated, astronomers identified additional large quasar groups and immense arcs of galaxies stretching across billions of light-years. Each new finding forced theorists to revisit their models of structure formation. How does something so large form? How can matter clump coherently across such vast distances when the early universe was so uniform? Are these structures statistical flukes? Or do they hint at physics we do not yet fully understand? The formation of structure in the universe is governed by gravity acting on tiny fluctuations in density. After the Big Bang, the universe was nearly uniform, but not perfectly. Slightly denser regions attracted more matter, growing over billions of years into galaxies and clusters. Dark matter plays a crucial role in this process. It does not emit light, but its gravitational influence shapes the cosmic web. Simulations of cosmic evolution show dark matter forming filaments and nodes remarkably similar to what we observe. Yet simulations also suggest limits. There is a characteristic scale to structure growth. Beyond a certain size, fluctuations average out. The larger the volume, the closer it should approach the cosmic mean. So when astronomers report structures stretching billions of light years, it forces a tension between observation and theory. Are these truly single structures, or are they chance alignments of smaller groups? The definition matters. Statistical methods are used to determine whether such structures exceed what would be expected in a random distribution. In some cases, debate follows discovery. Independent teams reanalyze the data, testing whether the claimed structure remains significant under different criteria. Sometimes the structure holds. Sometimes its size shrinks under stricter definitions. This is the nature of science. Claims of cosmic superstructures are not accepted lightly. And yet, the pattern persists. The universe contains structures far larger than we once imagined possible. To appreciate their enormity, consider the observable universe itself. Its radius is about 46 billion light years. Not because the universe is 46 billion years old, but because space has expanded while light was traveling. The total diameter is therefore about 93 billion light years. A structure 4 billion light years across occupies a noticeable fraction of that span. It is not a trivial ripple. It is a continental plate in the architecture of the cosmos. When we speak of the largest object ever found, we are confronting the edge of our models. We are asking whether the universe remains similar at all scales, or whether there are rare, colossal features that defy simple statistical expectations. Because the largest object ever found in the universe did not appear as a glowing beacon in the sky. It was not seen through a telescope as a bright shape against darkness. It was uncovered slowly, statistically, painstakingly, by mapping millions of distant objects and allowing patterns to emerge from what first appeared to be chaos. For most of the 20th century, astronomers had only a partial map of the universe. We could see galaxies, measure their redshifts, and estimate their distances, but our view was incomplete and fragmented. It was like trying to understand the geography of Earth by standing in a single forest and assuming it represented the entire planet. Then redshift surveys changed everything. When light from a distant galaxy travels toward us, the expansion of the universe stretches its wavelength. This phenomenon, known as cosmological redshift, allows astronomers to determine how far away that galaxy is. The greater the redshift, the farther the galaxy, and the further back in time we are observing it. By measuring redshifts for millions of galaxies, scientists began constructing three-dimensional maps of the cosmos. One of the most transformative efforts in this endeavor was the Sloan Digital Sky Survey. Conducted by the Sloan Digital Sky Survey, over decades it cataloged the positions and distances of millions of galaxies and quasars, providing an unprecedented view of the large-scale universe. What those maps revealed was not randomness. Instead of galaxies being sprinkled evenly throughout space, they were arranged in a vast network. Filaments stretching across hundreds of millions of light years, intersecting at dense nodes filled with galaxy clusters and surrounding enormous voids where relatively little matter exists. This structure became known as the cosmic web. The cosmic web is not metaphorical. It is a literal, measurable arrangement of matter shaped by gravity over 13.8 billion years. Computer simulations of cosmic evolution incorporating dark matter and dark energy had predicted such a network. But seeing it emerge from real data was something else entirely. To visualize it, imagine a three-dimensional spiderweb on a scale of billions of light years. The strands are composed of galaxies and dark matter. The intersections are clusters containing thousands of galaxies. The empty spaces between strands are cosmic voids, regions sometimes spanning hundreds of millions of light years with only sparse galaxies drifting within them. The existence of the cosmic web confirmed that gravity, acting on the faint density fluctuations imprinted in the early universe, had amplified those fluctuations over time. Regions that were slightly denser attracted more matter. Matter streamed along filaments toward gravitational wells, forming clusters at the intersections. But the web also raised a new question. If the universe is supposed to be homogeneous on the largest scales, how large can these filaments and walls become before they violate that principle? The cosmological principle asserts that the universe, when viewed on sufficiently large scales, should appear uniform. Not perfectly smooth, but statistically similar in all directions. This assumption is embedded in the equations derived from general relativity that describe cosmic expansion. Yet as surveys expanded, astronomers began detecting structures whose sizes approached, and sometimes exceeded, the theoretical scale of homogeneity. One of the earliest dramatic discoveries was the CFA Great Wall, found in 1989. It stretched roughly 500 million light-years. At the time, it was astonishing. It suggested that matter could organize itself into structures much larger than galaxy clusters or even superclusters. Then, in 2003, the Sloan Great Wall was announced, extending nearly 1.4 billion light-years. It was not a single gravitationally bound object, but rather a vast arrangement of galaxy clusters and filaments forming a coherent overdensity. Each new wall forced cosmologists to revisit their models. But the most extreme candidates for largest object status would not come from galaxy surveys alone. They would come from quasars. Quasars are among the brightest objects in the universe. Powered by supermassive black holes accreting matter at the centers of galaxies, they can outshine entire galaxies. Because they are so luminous, they can be observed at enormous distances, billions of light-years away, allowing astronomers to probe the distant universe. Importantly, quasars are not randomly distributed. They trace the same large-scale structure as galaxies. Where matter is denser, quasars are more likely to form. By mapping quasars across cosmic time, researchers identified enormous groupings known as large quasar groups. These are collections of quasars clustered together more densely than the surrounding cosmic background. In 2013, a team analyzing quasar data from the Sloan survey announced the discovery of what they called the Huge Large Quasar Group. The name itself reflected the shock of its scale. It spanned roughly 4 billion light-years in its longest dimension. 4 billion light-years. To understand what that means, consider this: the Milky Way is about 100,000 light-years across. 4 billion light-years is 40,000 times larger than our galaxy. Light leaving one end of this structure would take 4 billion years to reach the other side, nearly a third of the age of the universe. Such a structure challenges the expectation that beyond about 300 million light-years, the universe should smooth out statistically. Critics questioned whether the structure was truly coherent or simply an artifact of how the data was grouped. Statistical significance in cosmology is delicate. Slight changes in grouping algorithms can alter the apparent size and coherence of a structure. Yet the existence of extremely large quasar groups remained difficult to dismiss entirely. Similar large-scale alignments appeared in other analyses, suggesting that while the precise dimensions might be debated, enormous structures were indeed present. And then came another astonishing discovery. In 2021, astronomers reported a structure referred to as the Giant Arc. This arc of galaxies, located roughly 9.2 billion light-years away, appeared to span about 3.3 billion light-years in length. It was identified through statistical analysis of galaxy distributions, forming a curved shape across the sky. A curved structure billions of light-years long. If confirmed as a genuine physical feature rather than a statistical fluctuation, such a structure would push against the limits of our cosmological models. The key issue is this: the cosmological principle does not forbid large structures. It only states that on sufficiently large scales, the universe should appear homogeneous. The debate centers on what sufficiently large means. If structures approach several billion light-years, they may challenge the predicted scale of homogeneity derived from cosmic microwave background measurements and large-scale simulations. The cosmic microwave background, observed in exquisite detail by missions such as the Planck, reveals minute fluctuations in temperature across the sky. Those fluctuations represent density variations in the early universe, only about 380,000 years after the Big Bang. From those initial conditions, cosmologists run simulations forward in time, incorporating dark matter and dark energy. These simulations produce a cosmic web remarkably similar to what we observe. But even the most advanced simulations predict a characteristic scale beyond which matter distribution should average out. When observations approach or exceed that scale, two possibilities emerge. The first is that the structures are statistical outliers, rare but not impossible fluctuations in a vast universe. Given enough volume, even unlikely patterns can occur. The second possibility is more provocative. It suggests that our understanding of cosmic structure formation may be incomplete. Perhaps dark matter behaves in subtle ways not fully captured by current models. Perhaps initial density fluctuations were slightly different than assumed. Or perhaps we are misinterpreting the data due to observational biases. It is crucial to emphasize that no confirmed discovery has yet overturned the cosmological principle. The universe, on the largest scales measurable with current techniques, still appears broadly homogeneous. But the tension introduced by these enormous structures keeps cosmologists alert. The largest object ever found is not just a record-breaking statistic. It is a stress test of our theoretical framework. And there is another layer to this story. When we observe distant structures billions of light years away, we are not seeing them as they are today. We are seeing them as they were billions of years ago. Light takes time to travel. The deeper we look into space, the further back we look in time. This means that some of the largest structures identified are snapshots of the universe when it was significantly younger. Their existence at those epochs constrains how quickly structure can form. If a structure several billion light years across already existed when the universe was only a few billion years old, it implies that matter clumped together remarkably efficiently. Dark matter again becomes central. Because it interacts primarily through gravity, it began collapsing into structures earlier than normal matter, which was initially coupled to radiation. After the universe cooled and neutral atoms formed, normal matter fell into the gravitational wells created by dark matter halos. The interplay between dark matter, dark energy, and cosmic expansion determines how structure grows. Dark energy, which accelerates the expansion of the universe, acts to suppress structure formation on very large scales. Gravity pulls matter together, dark energy pushes space apart. The largest structures we observe today represent the outcome of this cosmic tug-of-war. So what then qualifies as the largest object ever found? It depends on how we define object. If we require gravitational binding, then galaxy clusters might claim the title. But clusters are far smaller than the largest walls and quasar groups. If we define an object as a coherent overdensity, a region statistically denser than average and identifiable as a structure, then the largest quasar groups and galaxy walls become contenders. At present, the huge large quasar group remains one of the most frequently cited candidates for the largest known structure, spanning roughly 4 billion light-years. The giant arc and other large-scale alignments rival it in scale. Each of these discoveries emerges from the same cosmic web. They are not isolated anomalies, but extreme expressions of a universal pattern. The cosmic web itself may be the true largest structure, a network spanning the entire observable universe. But because it is continuous and pervasive, we do not describe it as a single object. Instead, we identify its most prominent features. In this sense, the largest object ever found is a crest in a cosmic ocean. The universe is not merely vast. It is structured on scales that strain the limits of comprehension. And somewhere within that structure lies a formation so immense that even galaxies become minor details in its shadow. If you've been fascinated by the scale and mystery of the universe so far, don't miss what's coming next. Subscribe to The Boring Universe to join us on these deep cosmic journeys. Hit the like button if this exploration blew your mind, and leave a comment below telling us which part of the country you're watching from.